All right, so today we are looking at Quiz 7 review. So first I'm saying factor completely. So when I see this first problem, first I want to look for a GCF. I don't see one. So now I'm looking to see if this first term and this second term, if they're perfect squares or perfect cubes. And I can see that they are both perfect squares. So here this is really 25 x to the fourth power as a quantity squared, and here is 16 squared. So I really have a difference of two squares pattern. I can write it as 25 x to the fourth minus 16 times 25x to the fourth plus 16. I know there's nothing more to do here. There is no sum of two squares, only a difference of two squares. And over here, these are both still perfect squares. So I can do one more breakdown into 5x squared minus 4 times 5x squared plus 4, and then 25x to the fourth plus 16. Now that is fully factored. Nothing else I can do to break that down. Okay, next one I'm looking to see, again, there's two terms, there's a plus in the middle. Are these perfect cubes? Well, right here, right, 64 is 4 cubed, and x to the sixth power is x to the second power cubed. 343 is 7 cubed. So yes, I'm going to just write out what it is that's being cubed. All right. So 4x squared as a quantity cubed, 7 cubed. So I have a sum of two cubes. So I'm going to write that 4x squared and 7 together. That's my small parentheses. Then I take that first part right here. I square 4x squared. So 16x to the fourth. The product between the 4x squared and the 7. So 28x squared in the middle, and then 7 squared is 49 right here. Then I think of SOAP, so same sign, opposite sign, always positive. And that's as factored as I'm going to get. Okay, last one over here. I see three terms. I do see a GCF. They're all divisible by 2 and x to the fifth power. So I'm going to divide out 2x to the fifth power from all of the terms, leaving behind x to the eighth plus 5x to the fourth plus 4. So now looking at what's left behind, I recognize that this is quadratic-like. My highest degree of 8. Next, it's half of that power, 4, and then my constant. So that would be the same if I had a power of 4, power of 2, constant. Power of 6, power of 3, constant. Those are quadratic-like. I'm going to rewrite that 2x to the fifth. And then I know that my parentheses, I have an x to the fourth in the first two spots. So now what multiplies to 4 that adds to 5? And it has to be a 1 and a 4 with a plus in both spots. And then that's it. That's all I can do. Fully factored. Okay, next up here I'm saying determine whether x plus 5 is a factor of this polynomial function. So two ways that I could check. I could use substitution. So if I use substitution, let me just write that out first. Right, I'm looking for, is x equals -5 a solution? Is it a 0? So if I input an x value of -5, is it going to output a remainder of 0? So if I use substitution, let me plug in f of -5 equals 3 times -5 to the fourth power plus 15 times negative 5 cubed minus negative 5 squared plus 25. Okay, so 3 times negative 5 to the 4th plus 15 times negative 5 to the 3rd minus negative 5 squared plus 25. That will output to 0. So yes, this is a factor. Negative 5, 0 is a point on the graph. Okay, if instead you wanted to use synthetic division or long division, that works too. Let's show you synthetic division again. So here I would be dividing out again the solution of negative 5. Okay, transfer all of these coefficients. Use a placeholder if something isn't there. So 3, 15, negative 1, 0 for that linear term, and then 25. Okay, bring down the 3, multiply, add down, multiply, add down, multiply, add down, multiply, add down. Okay, so here again I'm showing a remainder of 0, and that confirms that negative 5, 0 is a point on my graph. And when I use synthetic division, I'm actually showing now what's left over, right? This would be the cubic term, and then the quadratic, linear, and then the constant. Okay, next skill. Can you solve polynomial equations? And a reminder that you should have as many solutions as your highest degree. You just might have a multiplicity of 2 or a multiplicity of 3. You might see the same solution multiple times. All right, so looking right here, my first thought is let's get everything onto the same side. Let's subtract that 27x to the 3rd. So I have 9x to the 5th minus 27x to the 3rd equals 0. Okay, now looking at it, I see that I have a GCF. They're both divisible by 9 and by x to the 3rd. So I'm going to divide that out, leaving behind an x to the 2nd minus 3. So now when I solve, I can set each factor equal to 0 and keep solving. So over on the left, if I divide out a 9, I get x to the 3rd equals 0. Okay, take the cube root of each side, and I just get a solution of 0, right? Now, if I was graphing this, then I'd say, oh, it has a multiplicity of 3. Okay, over here, I have x squared minus 3 equals 0. So here I would add the 3 to the other side. Solve by taking the square root, and I get plus or minus the square root of 3. So I'm seeing that I have a solution at 0, right? Graphically, that would be a multiplicity of 3. And then I have a solution at root 3 and at negative root 3. Okay, so again, if I was graphing this, it would slice through at the origin, right? And it would have a little wiggle when it slices through because of that multiplicity of 3. Okay, this next one here, when I stare at this, I see, oh, well, these are both cubes joined by subtraction. Right, x cubed, 5 cubed. So factor it out, x and 5. The x gets squared, product of the 2, the 5 gets squared. Okay, follow the SOAP, same sign, opposite sign, always positive. I get a solution at x equals 5 really quickly, but over here I still need to solve this one. I would probably use quadratic formula, so I'm looking at x squared plus 5x plus 25 equals 0. So here I'd plug in x equals negative 5 plus or minus the square root. The b gets squared, so 5 squared minus 4, a is 1, c is 25, all over 2 times 1. Okay, as I clean this up, I get negative 5 plus or minus the square root. I have 25 minus 100, so negative 75 all over 2. Okay, square root of negative 75, negative 5 plus or minus, well, 75 is 25 times 3, so I have 5i root 3 all over 2. And there's really nothing else I can do to simplify that, so that stays as is. So I have a solution at 5, and then here are my other two solutions. Negative 5 plus or minus 5i root 3 all over 2. All right, next up, factor then graph. Helps to see in factored form so we can graph. First step though, I notice that there's a negative 1 out in front, so I'm going to go ahead and divide that out. That is my GCF. It just flips everything to the opposite sign. Okay, now I see that I have a 4-term polynomial. The only way that I can break that down is by grouping. So group the first two and then the last two. So my GCF here is x squared, leaving behind an x plus 1. Over here, a negative 9, leaving behind an x plus 1. These match. Regroup it. X squared minus 9 times x plus 1. Right, difference of two squares, so keep going. X minus 3, x plus 3, x plus 1. Don't forget that we divided out a negative 1 first. Let me just rewrite it as a function. So fully factored function right there. So my x-intercept's pretty easy to see. I have 3, 0, negative 3, 0, negative 1, 0. And then my y-intercept, right, if x is 0, all of that goes to 0 with a 9. So if I plot those points, right, I have my 3, 0, negative 3, 0, negative 1, 0, 9, right about there. I also see that it's negative, right, negative and odd. Okay, so I'm going to start high and end low. Okay, ends up looking just like this. Again, we're just looking at end behavior and the right intercepts. Add your labels. All right, all looks good. Okay, the next one here, we see that it is here first, GCF, right? Everything here is divisible by x to the 4th. So divide that part out first, x to the 4th. And then x squared minus 11x plus 30. Okay, so now here I see, oh, that's just a basic quadratic trinomial. What multiplies to 30 that adds to negative 11. So here g of x equals x to the 4th, and then x minus 6, and x minus 5. Okay, fully factored, but here I'm going to have a multiplicity of 4. So my x-intercepts, origin, right, again, multiplicity of 4, just means it's going to bounce there and be a little bit wider than it would have been if it was x squared. 6, 0, and 5, 0. Okay, my y-intercept, if it passes through the origin, that's my y-intercept also. So plotting a point here, that's where it's going to bounce. And then 5, 6, like that, right? Positive, even, right? So positive and then even highest degree. So here I'm going to start high, come bounce, pass through, and then back up like so. 0, 5, 6, labeling those intercepts. All right, flip it over. Let's go to the back. Okay, circling back to polynomial inequalities, so very similar to how we were doing it when it was just quadratic inequalities. Now we just have a little bit more squiggle to it. And I recommend a graphical approach. The number line is fine too, but graphs are so easy. So first thing that I'm doing when I look at this polynomial inequality is I'm looking for where those roots are. Where are the zeros? Where would be the x-intercepts? So right here I'd see, okay, well x would be 3, and here x would be -4. A reminder that this would produce a multiplicity of 2. So graphically it's going to bounce there. So if I make a little sketch, let's see, here is my -4 and my +3. I like to circle to remind myself it's going to bounce. Okay, I know that here is where y equals 0, right? My function would be equal to 0. Here's where my function would be more than 0, where the y's would be positive, and here's where they would be negative. So when I do my little sketch of it, right, it's negative and odd. So I'd start high, come up, bounce, and then end low. Right, this is what my function would look like. Here is where y is equal to 0, and it can be equal to 0, so I'm going to fill that in, make that solid. And then I'm looking at where it's more than or equal to 0. So the only place where it's more than 0 is right here. So when I write that as a solution, I would say, right, that's -4 and that's 3. I'd say from -infinity to -4, hard bracket on that -4, union with this lone discrete value of 3. And if I'm saying one individual value, I can put it in those fancy brackets. I could also just state x equals 3. That would be fine too. Right? If I just wrote that as x equals 3, no problem. You're just showing that it can be this spread of values and then also this one individual value at 3. Okay, this one is similar. We just have to factor it first. So the first thing that I can see is that they're all divisible by x. That's my GCF. Leaving behind an x squared plus x minus 6. Less than 0. Okay, keep factoring it. What multiplies to -6 that adds to 1? Got to be a 3 and 2, where the 3 is positive, the 2 is negative. And then when we solve, we get x equals 0, x equals -3, x equals +2. So make a sketch. Again, here is where my function equals 0, right? The y values equal 0. Here's where they're more than 0 and less than 0. So here is the x-intercept at 0, 0, 2, 0, -3, 0. It is cubic, so odd and positive. So start low and high. Okay, right here is the -3, 0, and 2. Now we're saying less than 0, not equal. So all of these intersections are hollow, right? Those x-intercepts right there, it will be hollow there because that's where my function equals 0. And then it's saying less than. So I'm looking at anything that is less than 0, which would be this region. So my solution would be from -infinity to -3, union with 0 to 2. For any of these values in this spread of options, that would make this a true statement right there. All right, next up, write a polynomial function of least degree using the information in the graph. So make it factored in standard form. So what can I pull from the graph? My x-intercepts, right? I have -1, 0. It's bouncing there. So multiplicity of 2. And then right here, 2, 0. So it looks like it's negative and cubic if I'm looking at least degree. My y-intercept right here is at 0, 2. Right? And that's just a point on the graph, one of many points on the graph. So when I make my structure, I know that y equals a, right? I need to know any stretch factor or any flip. Right here, I need to know if it's going to be starting high, ending low. So I anticipate that that a should be negative. Okay, and then if I plug in those solutions as factors, I'd say that that is going to be x plus 1 twice, and then x minus 2. Okay, I need to find a. So I'm using this point, the y-intercept, when x is 0, y is 2, to find the a. So here's 2 equals a times 1 times 1 times -2. So 2 equals -2a. So it looks like a is simply -1. That's easy enough. So if I write this now in factored form, -1, I have y equals -1 times x plus 1, quantity squared, times x minus 2. Okay, but then I'm saying, oh, I want to see it in standard form also. So can you multiply it back out? So if I rewrite this as 2 separate factors, and then the x minus 2 with it, I would FOIL this part out first because I know that that is a perfect squared trinomial when I multiply it out. Right, it's x squared plus x, so 2x, and then plus 1. And then I have to multiply that by the x minus 2. Don't forget the -1 out in front as well. So when I multiply this out, I'm going to distribute that x over these 3 terms. So x to the third plus 2x squared plus x. And then same thing with that -2. So here I'll have -2x squared minus 4x minus 2. So as I clean this up, I have x to the third, right? Those quadratic terms cancel away. X minus 4x is minus 3x, and then minus 2. Don't forget the negative that was out in front. So y equals -x to the third plus 3x plus 2. All right, so there's my standard form. Okay, one more problem. So same idea, but I'm not giving you a graph. I'm telling you a point when x is 0, y is 16, also the y-intercept, and these are zeros. But remember that your roots come in pairs, and so do your imaginary solutions. So you really do have 2 other solutions here, -√3 and +4i. So this means that of least degree, this would be quartic. So first, let's just plug in what we know. Right? Y equals a times x minus √3, x plus √3, x plus 4i, x minus 4i. Okay, and now if I plug in the 16 for y when x is 0, I'm going to solve for a. So I have -√3, +√3, 4i, -4i. Okay, -1√3 times √3 is just going to be -3. Here I have -16i squared, and remember that I squared is -1, So really this is going to become just 16. So 16 equals a times negative 3 times 16. So I have negative 48a. And when I divide that negative 48 away, a is negative 1/3. So y equals negative 1/3. Okay, we don't usually write it like this. We actually would multiply that back out and write that as x squared minus 3. And then same thing here. We would actually multiply that back out and still say that this is factored form, and that would give us x squared plus 16. So this is factored form. It's just when we set these equal to 0 and solve, this is where we get that plus or minus root 3, and this is where we get that plus or minus 4i. Okay, and then lastly, can you multiply out the whole thing? Okay, which means we're going to FOIL this out first and then distribute the negative 1/3. So first, outer, inner, last. So I have x to the 4th plus 16x squared minus 3x squared minus 48. So x to the 4th plus 13x squared minus 48. And then distribute that negative 1/3. So y equals negative 1/3 x to the 4th minus 13 over 3x squared plus 16. All right, so good exercise in writing equations in factored and in standard form. Last skill, can you use the rational root theorem to factor completely, then solve for all zeros? Now, we're not going to give you one that's this complicated on the quiz, but good to practice a little harder than we're going to quiz you. So, rational root theorem, first thing to note is that this is the P and this is the Q. So we make a list of the possible rational roots. Right, so plus or minus P over Q. We need our factors of 4 and our factors of 1. Right, so 1, 2, 4, 1. So plus or minus 1, plus or minus 2, plus or minus 4. That's not a big list, but remember that we're going to have 5 total zeros. It's just that we might have a multiplicity of 2, maybe a multiplicity of 3 that we have to account for. So if I go in order, let's say I start with x equals 1. So f of 1 equals 1 to the 5th minus 3 times 1 to the 4th plus 5 times 1 cubed minus 1 squared minus 6 times 1 plus 4. So 1 minus 3 plus 5 minus 1 minus 6 plus 4 does get us to 0. So I just use substitution to see that 1 is definitely a solution. So let's divide it out using synthetic division. So transfer all of those coefficients. And let's divide it out. So bring down the 1, multiply, add down, multiply, add down, multiply, add down, multiply, add down, multiply, add down. Amazing, right? Just confirms it. So now what am I left with? So if I started with something quintic, now I have something quartic. So x to the 4th minus 2x to the 3rd plus 3x squared plus 2x minus 4 all equal to 0. I still can't factor it, so I need to look for another 0, another root. And again, I could have a multiplicity of 2, maybe even 3. So let's try 1 again. Let's try x equals 1 again. So if I plug in f of 1, right, I'm just looking at this new function. Whatever I want to name it is fine. So I'll say f of 1 again, but I'm looking here. So 1 to the 4th minus 2 times 1 cubed, 3 times 1 squared, plus 2 times 1 minus 4. 1 minus 2 plus 3 plus 2 minus 4. Ooh, looky there, gets me 0 again. Perfect. Let's divide out that second solution of 1. So here I have 1, negative 2, 3, 2, and negative 4. All right, bring down the 1. Multiply. Add down. Multiply. Add down. Multiply. Add down. Multiply. Add down. Right? Just confirms it. And now what is it that I have left over? So now, since I divided out a solution, and I was starting with something quartic, now I have something cubic. So I have x to the 3rd minus x squared plus 2x plus 4 equals 0. And I cannot factor that yet. Oh, so I need to do it one more time. I need to figure out what is one more solution. And I'm just going to remind you, again, we're not going to quiz you this hard. We're not going to give you this many ones to pull out, but good to practice harder than we're going to quiz you. Okay, so here's where I'm at right now. So maybe I have another solution at x equals 1. Maybe I have a multiplicity of 3. Let's check. If I plug in a 1, what happens? So I'm plugging in 1 cubed minus 1 squared plus 2 times 1 plus 4. Well, that's going to output to be 5. So no, I don't have a multiplicity of 3. Move on. Let's try negative 1. So f of negative 1, so negative 1 cubed minus negative 1 squared, 2 times negative 1 plus 4. This will output to 0. So good, we found another solution. Now we divide it out. So I'm dividing it from here. So 1, negative 1, 2, and 4. Just transferring those coefficients. Okay, bring down the 1. Multiply, add down, multiply, add down, multiply, and amazing, confirms, zeros out, remainder of 0. So now what are we left with? X squared minus 2x plus 4. Oh no, not going to factor, but I still need to solve. So this one I would probably complete the square, but quadratic formula would be fine. So take away the 4 if you complete the square. Remember that we take that linear term, we split it, we square it, gets us 1. So x squared minus 2x plus 1 equals negative 4 plus 1. X minus 1, quantity squared, equals negative 3. Take the square root of each side. X minus 1 equals plus or minus I root 3. Add the 1 to the other side. All right, our last pair of solutions. So if we write this fully factored, we have f of x is equal to, we had these two solutions at 1, so we would say x minus 1, quantity squared. We had another one at negative 1, so x plus 1, and then here, x squared minus 2x plus 4. So fully factored. And then what about the zeros? What about the total solutions that we obtained? We had a 1 with a multiplicity of 2. We had a negative 1. We also had 1 plus or minus I root 3. These were all of our solutions for x, 5 total. All right. That is all I have. Let me slide that up to make sure you can copy that down. Have a good rest of your day.